In this Matlab video, we're going to be talking about how to create a power spectrum using Matlab. And we'll compare a couple of different codes. This is based on the code in the Matlab help guide. So if it looks familiar, that's why. At the beginning of the code, I've set my sampling parameters. So this particular signal is being sampled at 1,000 frames per second, or 1,000 hertz. And then I've created a period, I've created a length, and I've created a time vector for my signal. Then I've gone ahead and generated a random signal. And we'll go ahead and run the code, and it will plot so you get an idea of what that signal looks like. So here's the signal. It's two sine waves added together, but then I've added some random noise to it as well. So to figure out what those two frequencies that we found that the signal is based on, we can take the frequency, we can do a frequency decomposition using the Fourier transform. So that's the first thing we're going to do here. We're going to use the command FFT, and our signal is X. And so we'll go ahead and do that, and we'll plot the results. And you can see that you get this weird looking mess here. And the reason for the weird looking mess when you run the Fourier transform is that the Fourier transform returns imaginary numbers or complex numbers. They have both a real part and an imaginary part. So in order to analyze our data, we need to be able to just think about real parts when we're thinking about frequencies, because we have real frequencies. So one way to do that is to find the real, is to make all of the parts of the power spectrum real. We're interested in the real frequencies, so we'll take the absolute value of the Fourier transform signal and normalize the magnitudes in order to give us something between 0 and 1 for our magnitudes. And then we can go ahead and see what we get when we do that, and you'll see that we have here a plot that has a horizontal axis from 0 to 1500, and it has these two sets of spikes. But remember that in our signal we only put in two frequency components, so we should expect two sets of frequencies in our frequency component analysis as opposed to four. So the reason for that is that we have both this imaginary half of the signal and this real part of the signal, and we need to, they're mirror images, so we need to combine them together and just think about half of the signal. So to do that, we will go ahead and take half of the signal, the first half of the signal, and continue on, multiply that by 2 in order to get the full half of the signal, and now, or the full value of the signal, and now you can see here that our magnitudes have doubled. We're only going from 0 to 750, and this frequency component, instead of being 0.4 over here and 0.4 over here, is now 0.8 right here, and it's a little over 100. And then there's another frequency component a little bit over 200, and if we look back at the frequencies in the original signal, we'll see that there was a frequency of 2 times 80, or 2 pi times 80, and 2 pi times 137. So we get us to those two values. So then we can go ahead and we'll go ahead and plot a nice graph of that, or at least a nicer graph of that. And this would be the power spectrum for our signal. But if you want to consider signals that maybe have different lengths of sampling time, different parameters going in, it's actually more useful to consider something called the power spectral density instead of the power spectrum for your signal. So to calculate the power spectral density for a signal, we're going to again take the Fourier transform. This time I'm going to use the Fourier transform command a little bit differently. I'm going to choose the number of frequency bins, and just as a reminder, if you ever need to get help on a command, you can type help at the command window, or you can go up to the help navigator and you'll get help for those. So help, n is the endpoint FFT with padded zeros if x has less than n points, and truncated if it has more. So this is going to be truncated because x has more than n points. So we're going to go ahead and do the Fourier transform here. And then after we've done the Fourier transform, we get our signal y. And if we plot y, again, we again get something that looks like that. If we plot the absolute value of y, we get something that looks much shorter and more compressed because we only use 250 points, 51 points this time instead of the full length of the signal, which is what we used the last time, 1500 points. So we get the same two peaks, so we're doing the same thing. But now, instead of taking the absolute value, we're going to multiply by the complex conjugate and normalize by the number of frequency bins that we have. So again, last time we normalized as well by the number of frequency bins. The number of frequency bins was the length of our sample in the last steps of the example. And then I'm going to go ahead and define our frequency vector, again, based on the number of bins that we had. And I'm adding 1 because 0 is a bin. And then I'm going to calculate my frequencies, and I set the number, which sets the number of frequencies to plot. And so then we can go ahead and we will get ourselves a plot here of, so then we can go ahead and plot our output. And you'll see that we again get the couple of peaks that we were expecting over here. And just for comparison's sake, we can go ahead and plot the second one as well, and we will see that we have a similar kind of set of values that frequency spectrum we have, though the second component is higher this time, or is gone this time because of the sampling frequency that we did. So it's an idea, a little bit of an idea about how you use single-sided spectrum versus power spectral density. For what we're doing in EMG, you definitely want to use the power spectral density. And just to help you visualize why, here's a blog post that is looking at some different vibration exposures for jet aircraft, and you can see that their data is very, very similar. They're all amplitudes, and they're all different lengths of time. So the first sample is 10 seconds, or is 1,000 points, the second sample is 10,000 points, and the third sample is 100,000 points. So just different lengths of time that the data has been collected over. So the signals have different lengths. And here's a comparison of the FFT versus the power spectral density for those different signals. So you can see that at the higher frequencies, the power spectral density handles the drop-off much, much better. Then you can see much more clearly what's going on than the Fourier transform does. So hopefully that gives you a sense of why we'd use the power spectral density instead of the Fourier transform for our applications here. We're taking things in different time frames. So with that, bring your questions to class.